Thank you for joining this lesson. We're going to look at electromagnetic induction. And the first thing we are told is to state the Lenz'S law of electromagnetic induction. So the Lenz'S law of electromagnetic induction states that the direction of the induced EMF is such that the induced current which it causes to flow produces a magnetic effect that opposes the change producing it. The direction of the induced EMF is such that the induced current which it causes to flow produces a magnetic effect that opposes the change producing it. Then now we are given a figure shows a bar magnet being moved into a coil connected to a galvanometer in the direction indicated. So when this magnet bar or bar of magnet is pushed or moved into the coil which is connected to a galvanometer, state the observations made on the galvanometer when the magnet is moved into the coil at a steady speed. So we have the galvanometer. The galvanometer deflects, then falls back to zero. It will deflect to a maximum value and it will fall back to zero. This is because when the magnet is fully pushed into the into the solenoid, we will have what we call electromagnetic induction taking place. The magnetic field will induce an EMF which causes a current to flow in the direction which is opposite to the change producing it. So actually the deflection of the galvanometer will be to the right because the motion of the magnet is to the left. So the galvanometer will deflect in the opposite direction because we've just said, according to the Lenz'S law, the induced EMF produces a current which flows in the opposite direction to the change producing it. When the magnet is held stationary inside the coil, there will be no deflection. No deflection on the galvanometer. No deflection on the galvanometer. Then the next thing is, how is a transformer designed to minimize energy losses through flux leakage? Flux leakage is whereby the magnetism in the primary coil does not 100% link up with the secondary coil. Therefore, to minimize the losses, to minimize the energy losses due to the flux leakage, whereby the linking of the primary and the secondary coil is not 100%, then we can have the secondary coil being wound on the primary coil to increase the linking. Increasing linking means that reducing the leakage. So we have the primary coil wound on the secondary coil. Actually, it's the other way around. We should have the secondary wound on the primary so that immediately electromagnetic induction happens on the primary. It links immediately with the secondary which has been wound on the primary. So we will have the secondary coil being wound on the primary coil to minimize the leakages. The next question is on transformers again. The primary coil of a transformer has 2,000 turns and is connected to a 240 volts alternating current supply. The secondary coil has 400 turns. State with a reason the type of transformer. We are seeing fewer numbers of turns in the secondary than in the primary, and this will automatically be a step down transformer. Step down transformer. Reason being, we have fewer turns in the secondary coil than in the primary coil. Then we are told to determine the voltage in the secondary coil. To determine voltage in the secondary coil, we're going to use what we call turns ratio. We shall say the number of turns in the secondary divided by the number of turns in the primary should give us voltage in secondary out of voltage in primary. So we have number of turns in the secondary as 400, number of turns in the primary 2000. Then this should be equal to voltage in secondary, which is unknown, divided by voltage in primary, which is 240. So we can get Vs by cross multiplication, where we multiply with 240, 240, and voltage in the secondary coil is going to be, if I use my calculator, I'm going to have 400 multiplied by 240, then I divide with 2000. This gives me 48 volts exactly. So that will be the voltage in the secondary coil. Again, we are told if the current flowing in the primary coil is 0.5 amperes and in the secondary coil is 2.0 amperes, determine the efficiency of the transformer. For us to get efficiency of a transformer, we need to get power output divided by power input. Then we multiply by 100. So to substitute power input, remember generally power is VI. So power output is the power in the secondary. So power in the secondary is going to be the voltage there, 48, times the current there, which is 2. Then we divide by power input, which is power in the primary, and the voltage in the primary is 240, times the current there, which is 0.5. Then we express it as a percentage. 48 by 2 by 100, we divide by 240 by 0.5. This gives me exactly 80%. So this transformer is 80% efficient.